I would like to thank organizers for inviting me to give this talk, and I will proceed. So, it was shown by many authors that violation of Bell inequalities had not provided any proof of the non-locality of quantum theory. Strangely enough, these results seem to be neglected. Quantum non-locality, hereby the particles appear to influence one another instantaneously, even though they are widely separated. It's one of the most remarkable phenomena known to modern science. Today, it is a well-established experimental fact. Correlations are coming out of space-time. These statements you can find in the literature. We roll a pair of dice. Each die on its own is random and fair, but its entangled partner somehow always gives the correct matching outcome. It is impossible. Nobody understands quantum mechanics. If you continue to use imprecise language and incorrect mental images and analogies, nobody will ever do. Real magic of nature is, I would like to talk about migration of monarch butterflies. And here is migration from Ontario to Mexico. Finally, it was discovered how it happens. And this is how nice our butterflies, after 3,000 kilometers fly, they are wintering in Mexico. And this is very interesting, a calendar. So for example, if we start here, when monarch butterflies who came from Canada, they spent winter here. After they start going backwards, and they lay eggs somewhere here, and they die. The offsprings never met parents' butterflies. The children are coming to Ontario. After you have 2 generations, they die, they lay eggs, and finally, super butterfly is created, a new generation is created in August somewhere, which is migrating and is living much longer than the other ones. So what we can say is the magic that somewhat these patterns are coded, the memory of this is coded in our genes. So there is some kind of. Main points of this talk. QT is statistical theory describing phenomena and not individual systems having attributive properties. The probabilistic models used to prove Bell inequalities are inappropriate for description of spin polarization correlation experiments. The correlation and SPC indicate that nature is not playing dice, and also it could explain migration. QT is emerging theory. Perhaps it is not predictably complete, and we can test it. So this is the typical experimental data. We have beam, device, time series of outcomes. This time series is usually analyzed using histograms. And in quantum mechanics, we have state preparation, we have psi or density matrix rho, we have measuring apparatus, self-adjoint operator, and we have here probabilities. Does it provide a complete description of our phenomena? So very often, probability is misunderstood. So in this case, according, I think, to probabilists and statisticians, probability is a property of a random experiment. Probability is neither a property of the coin nor a property of the flipping device. It characterizes only a particular random experiment, flipping coin CI with a device DJ. So in this case, QT gives probabilistic predictions for distribution of the results obtained in long runs of one experiment, distribution of the results of several repetitions of the same experiment on a single system. QT is an abstract statistical and contextual theory. Einstein was the first to question it. The essential statistical character of contemporary quantum theory solely ascribed to the fact that this theory operates with incomplete description of physical systems. Psi function does not in any sense describe the state of a single system. God does not play dice. So statistical interpretation, we have identical state preparation, and with this we associate mathematical objects like wave function and density matrix. So irreducible randomness, which I will try to question here, and so any measurement causes the system to jump into one of eigenstates of the dynamic variable that is being measured. If a jump occurs, only the probabilities of obtaining particular experimental result can be calculated in theory. Outcomes of measurements performed on two separated physical systems are uncorrelated. So here we have famous EPR bomb model spin polarization correlation experiments in which we have a pulse of laser hitting the nonlinear crystal produces two correlated signals propagating in opposite direction. If you place polarizer in front of the detector, we obtain 2-time series of clicks on the far away detectors which are correlated. Einstein, Bohm, Bell. The correlations cry for explanation. It's true station. All local models, Bell inequalities. This is not true. So this is conclusion which is believed by many, that all local models imply Bell inequalities, what is not true. Okay. So let's see here this. So we have some source. We started, it's taken after Bell. We have here measuring apparatus X, Y. We have two signals coming here, S1, S2. We are giving outcomes A and B. And so how it's done, how we do data description. We have two samples, yeah, A1, A2, AN, B1, B2. Mathematical statistics, there are observations of 2-time series of random variables. If these random variables and some A are independent, identically distributed, and B, J are also identically distributed, then the outcomes of the experiments XY are completely described by the conditional probability distributions. This is a conditional probability distribution XY PAB, and it depends also on signals and things like this. And in general, if you have correlations, these probabilities do not factorize. So pure ensembles plus irreducible randomness imply no correlations. Why? If each signal is a pure statistical ensemble, for example, a beam composed of identical physical systems, and the local experiments XY are causally separated, and the outcomes of these experiments are obtained in a reducibly random way, then A and B are independent random variables. And we have this factorization, covariance is equal to 0. A classical model of this is tossing, we have dice, Alice has a dice, Bob has a dice, they are tossing them, and results, you can compare results. There is no time factor, will be no correlations. So correlations with irreducible randomness. However, in classical way, we can keep irreducible randomness and get correlations. For example, if the source is sending signals, S1, it's a mixed statistical ensemble. For example, that you are sending pairs of dice, which are particularly chosen, and it's a mixed ensemble, we can create correlations. And how it will be, we have to introduce some parameters which describing various components of the mixed statistical ensemble created by S. In this case, we get very nice equation. PABXY is P of lambda, lambda is, and we have PAX lambda 1, PBY lambda 2. This is, in stochastic hidden variable models, which are considered now to be more general than initial Bell model, this is called locality assumption. You see that it's nothing to do with locality. It's simply that we are doing with the mixed statistical ensemble of correlated physical systems. So other model, which was it's local relativistic hidden variable models. We have all properties are determined as a source. In measurement, a particular property is recognized. A mixed statistical ensemble of classical physical system. Classical randomness is created by the source. And this is we obtain this factorization. So lambda is unique probability space. P lambda is a joint probability distribution of ontic properties, non-depending on the choice of xy. This is so-called Bertelmann-Sox models because source is sending socks left and right. It can be in different colors. It can be different sizes. But, of course, you can have correlations, even perfect correlations. So these two models lead to, if this expectation values are smaller or equal to 1, we get this famous Clauser-Horn-Shimoly-Holt inequalities. And the inequalities are violated. And we have here Professor Weiss, who showed it. And usually, does it prove non-locality? No. This is my statement. I have to drink some water. What is randomness? Yes? So, knowing past events, we cannot predict future events. Classical randomness, fair core flipping, stock market price, reducible. The laws of nature are deterministic. We could control relevant factors. We would predict all the outcomes. Quantum randomness, spin projection, time of decay, is believed to be reducible. The laws of nature are not deterministic. It is impossible to explain and predict outcomes in a causal way. Experimental randomness, a time series of outcomes, satisfies all statistical criteria of randomness. This is randomness which you observe in testing SPCE. We test whether the outcomes appear in a random way. So perfect correlations of random local data. Different explanations. Spooky action at the distance between x and y. Correlations coming out of space. Passive measurements not destroying correlations. Local realistic hidden variables created the source. Mixed ensembles of Bertelmann-Sox. If we can have imperfect correlations, for example, stochastic hidden variable models, mixed ensembles of fair dice. We can also explain imperfect correlation by correlated signals created by the source, partial memory kept during the travel to the measuring devices. Outcomes are not predetermined, but are created during the measurements. Contextuality plus local determinism. So how it works, how it can be written as a probabilistic model. So we have what we add here. We add here, it's called extra supplementary parameters. Lambda 1 is describing the signal coming to the x, and lambda x are parameters describing the x. So we have here signal S1, measuring device x in a moment. In a similar way are produced, outcomes are determined in local deterministic way by the values of lambda 1, lambda x. So this is important, and how it translates to the model. So we have modeled the following. We have here some probability space, lambda xy and lambda are here. And we have here A, lambda 1, lambda x, B depends lambda 2, lambda y. They are plus minus 1, and we get P lambda is probability distribution of these parameters which describe signals and the parameters which describe devices. Now there is no common probability space lambda, and lambda xy are different probability spaces for each pair xy. It is impossible to prove CS, CH, and Bell inequalities. Simply impossible. To prove it, we had to have the same lambda. Yeah, so for example, in CSA-Bell proof, the existence of the common probability space was taken for granted. Here, this is different, and this is called by Theo, I think, fatal contextuality loop. So it was noticed by many people many years ago. Carr-defined, Hess-Krenikow, myself, Mikkelsen, De Moint, I could Theo and things like this. And a lot of contributions of André, I think, if you see it, it's And also I wrote many papers, but the other also contributed, wrote many papers on the subject. Vorobiev, somebody found, I think it was Hess, that in 1962, Vorobiev asked the question, is it possible to construct always a joint probability distribution for any triple of the only pairwise measurable observables? Answer was no. But quantum information community cannot or does not want to understand it. Perhaps magic sells better. What is the conclusions? Violation of CSSH implies no irreducible randomness. If it would be irreducible randomness, all correlations created as a source would be destroyed. So if you have no irreducible randomness, it means the probabilities of quantum theory should be explained, can be explained by some emergent, for example, by some subquantal theory. So it suggests perhaps that emergent QT, the QT is emergent. Okay. So correlations imply emergent quantum theory. So in this case, each pure quantum statistical ensemble is a mixed statistical ensemble. Perhaps there is more information in the data than predicted by QT. Is QT it's predictably complete? It's a question. And typical experimental data, we come back, beam device, time series histogram. State preparation, the question is, does this provide a complete description of the data? So purity tests to test completeness of quantum theory. If the mixture is not perfect, then by changing the intensity or geometry of the beams, we may obtain a sub-ensemble having slightly different properties than the initial ensemble. Using purity tests, we may detect this effect. Okay. So what is the data description? This is by quantum theory. We saw this slide. I will see what is the modification. The conclusion was that we can use conditional probability distribution. If there is more information in the data, we have the following situation. We have the same thing, and now all these random variables are not independent and identically distributed. And all BI and B are not identically distributed. Then the outcomes of the experiment XY are not completely described by the conditional probability distributions. We have time series. So the idea is to look for the fine structure of time series. Let us consider a random experiment which can give only two outcomes, 1 minus 1, 1 minus 1. By increasing value n, the relative infrequency getting 1 can reach 1/2. Of course, this is not complete description of the time series. We can have another example, which is a bit complicated, but if you look well, you see some structure. So descriptive statistics, histograms, all fine stochastic structure is destroyed. So to find out some fine structure in the data, we have to proceed in more detailed way. And how we can do it? So the question now, what will be this quantum theory predictably complete? If answer is yes, it means that the time series of experimental data are completely described by the probability distribution given by QT. It has to be tested, not taken for granted, purity test or time series analysis. So how we can analyze visualizing correlations in the autoregressive time series? We have to make simple time series plots, ZT, lagged scatter plots, sample autocorrelation function plots, and many techniques which were invented to study time series of data. So we did also to illustrate that fine structure of time series is destroyed by calculating histograms or doing descriptive statistics. We simulated a sample of 500 of some autoregressive time series, which was given. This is random variables, and this is given this formula. And we make standard descriptive analysis, histogram, normal score, summary, and things like this. And it was consistent with normally distributed population. Only the detailed time series analysis allowed to discover a fine structure in data. So for example, we went here. This is a normal score test, which usually is a test of normality of our distribution. And here are partial autocorrelation function. You have a statistical software which gives you enter the data and it gives you this. And you see here these two contributions which were showing the structure of this autoregressive time series. So conclusion, violation of CSE, no irreducible randomness, and we have emergent quantum theory. And nature is not playing dice. What I wanted to say, completeness, is Qt predictably complete? It is an open question. More you can find here, where you can find a reference to my papers, but you have in any paper reference to many other papers on the subject. And sometimes we are saying that Bohr didn't understand it because people are saying that Bohr was saying that quantum mechanics gives a complete description of individual physical system. But if you read this, you see that Bohr was very cautious. He told, strictly speaking, the mathematical formalism of quantum mechanics and merely offers rules of calculation for the deduction of expectation pertaining to observation, obtained under well-defined experimental conditions specified by classical physics. There was nothing said that it's a complete description on the visual systems. And I think I have other slides, but I think it's better perhaps to leave time for discussion. Thank you.
Thank you. We have plenty of time for discussion. So I'm sure there's some.
If there's no discussion, I will show you how to work purity state, purity tests. No. Yeah.
So I think I have to react because we have people sitting here.
Yeah, of course.
So you said there's kind of an insinuation that quantum formation sounds magic through.
It is not an insinuation, but what I am saying in general, magic is selling better than something which is not magic.
So Bell's theorem is a mathematical theorem. It has certain assumptions from which you derive violation of Bell inequalities. Now, what you are doing here, by introducing a lambda that depends on measurement settings, x and y, is not a part of the assumptions of Bell's theorem.
Of course.
So if you change the assumptions of Bell's theorem, then you can prove whatever you want, of course. It has no relevance for Bell's theorem.
No.
Thank you very much.
No, what I'm objecting, Bell thought that it's the most general local description. And he did not understand that it's not true, that simply, if you incorporate properly the parameters in each experimental settings, there is no common probability space, lambda, which he was using in his proof.
Let me ask, if you are the experimenter, are you controlled by those hidden variables? You?
No, of course.
No, you're not? Okay.
Well, what is controlled? I'm not controlled, no.
You are controlled, because you have to include yourself in those parameters.
No.
Yes,
the problem is that you don't need person. No, you have a measuring apparatus.
Oh, I'm the measuring apparatus. I sit there, I turn it.
Yeah,
you're saying I'm controlled by the hidden variables.
No,
Okay.
no, I'm not saying this. Could I say better?
But I use what I set as the parameter. I don't care what happens inside the machine. Huh?
No. What I'm saying, a machine is, you get a click after photomultiplication for some machine is there. You have a signal, hitting some first detector, passing by polarizing like this. It perceives this polarizer.
Sure.
Is described by some internal structure. And in the moment of when signal is hitting this polarizer, things happen. Finally, you get an outcome. This outcome is determined by state of the apparatus in the moment of the impact of the signal and state of the signal hitting the apparatus.
Sure, but that's just randomness, right? You just add randomness, local randomness. No?
No, it's not. It's no. I'm not adding local randomness because I don't know this distribution.
Sure, no, but I don't care because all I care about is the parameter I set. You know, whatever extra randomness stuff goes on, I don't care. It can only
only
ruin
I am going for some quantal description of your you put your, of course, you fix it, you measure in this direction, but your apparatus is described in this case.
It doesn't matter.
It matters.
No, it doesn't matter.
It matters because probabilistic model which you have deterministic outcome, which is caused by parameter which describes the state of apparatus is the moment of the impact,
so
and the signal, and other parameter describing the signal in the moment of the impact. So in this case, an outcome is deterministic depending on this two.
And it can depend on many other things. But if you only add random stuff, how do you actually, what is your feeling? Are there correlations or are there no correlations?
Of course, you
there
have
are
correlations.
But so by adding more random stuff, can I get more correlations?
No, correlations are not perfect. You are not getting more correlations. The correlations are created by the source.
They're
in mathematical proof of the the correlations are created at the moment by it's in the source, and they are imperfect. Okay.
So if they're created by the source and I add more random stuff, can they
are
improve?
They are less perfect, but in this case, mathematical model which you are using, you are not allowed to use.
I don't care about the model.
No.
Actually, what is quite nice is that the next presentation, which is mine, is actually going to talk about that problem. So
we still have 3 minutes, so we're good. Let's talk. Let's ask Andre.
Okay.
Suppose Niels Bohr will come to this room now. My impression is that he will support Marian, because Marian told that we should take into account all experimental arrangement. It's position of Niels Bohr. So surprisingly now, Marian, who criticized Bell's theorem, I think in the orthodox Copenhagen position, and those who disagree with him really go against Copenhagen. So this is my viewpoint. Because Bell did not take into account measurement arrangement. It's only message of this talk. Take into account that there exists measurement apparatus, and situation will be more complicated. I do not agree maybe with Marian that it's so trivial, that by including, because I spent a lot of time trying to construct realistic models.
It's not constructive. It doesn't explain anything.
So there is no construction.
Says,
But in any event, criticism, I think, well acceptable from Copenhagen position. Where is measurement device in Bell's theorem? No.
Excuse me, can I tell something?
Yeah.
The Bell theorem is a mathematical theorem based on some assumption, and it is probabilistic theorem. Yeah. And this is based, like you told, on some assumption of existence of the common probability space lambda, in which you can describe all local experiments.
For sure.
The problem is that this unique probability space does not exist.
I think we all
does
agree
not
on
exist.
That. We all agree on that.
So simply, so simply, the Bell theorem cannot be proven if you take into consideration.
No, I agree, but that's irrelevant, I think, because it's not, you know, there's a lot of things I cannot prove.
No magic.
No, there's a lot of things I cannot prove. Yeah, now we're over time. Okay, one more.
No, I wanted simply to say that I completely agree with Bruckner, but I wanted to strengthen this position by claiming that, by remembering a sentence that Bell had repeated at least 100 times since I knew him. He has always stated, I started from the EPR complete correlation, and through my locality request, which is a precise mathematical request, I got to deterministic hidden variable theories. But all people start from hidden variables to go to Bell inequality. And if you add that variable, you are not following Bell line of thought.
I'm following Bell line of thought.
But
simply, I am showing that his model is not general enough, and he didn't notice it, and this is why. And this is why Bell inequalities cannot be proven. And in this case, they are irrelevant in some sense. Okay.